The second case study is medical. Again, here the key challenge is to basically in the current process, multiple energy intensive and chemical steps are involved, such as grid blasting and masking, powder coating, sintering, and HA coating as well, in order to impart a different roughness and also bioactivity on the implant. So because of these multiple steps, the production cost is increased, and due to the powder coating and other non-deterministic steps like grid blasting, the variability is more, and there is also contamination risk with the grid blasting as well. And accordingly, the adhesive and abrasive reducer deposited on the coat because of the coating, and that will impact the biocompatibility. And in the SYNTECS project, laser surface texturing is intended to replace all these conventional steps with a single controllable laser hierarchical texturing with the micro and nanoscale textures that will give rise to different functionalities like low energy use, elimination of the coating powders, and clean and more durable implants. So the key performance indicators or key objectives in this particular case study are to achieve a surface roughness similar to the sandblasting for different functionalities, and replace 4 mechanical and chemical steps with the hierarchical laser surface texturing. And as shown in this slide, the left of the slide shows an image where the conventional cleaning process has number of steps, including grid blasting to final visual inspection. And in different scenarios, we wanted to remove these number of steps with laser surface texturing. And these are some of the hip implants shown here. And the hip implants before the powder coating are shown in this particular image. So here, before the powder coat is nothing but titanium beads sintered onto the surface of this particular implant, and the sandblasting will be performed before the powder coat adhesion onto this particular implant. So we wanted to replace the sandblasting with the laser surface texturing. The first scenario was to achieve sandblast roughness with laser surface texturing in order to increase the increase the bonding strength between the powder coat and rough surface. And in the second scenario, why not simply replace the powder coating with the laser surface texturing? That is also we have investigated in this particular use case. And this particular slide shows that we have different surface roughnesses are produced akin to the grid blasted roughness as shown here with laser surface texturing on cylindrical components, and powder coat has been sintered on these particular rough surfaces in order to test the bonding strength between the powder coat and laser surface textured surfaces. And all the cases, in all the roughness cases, what we understood is like the specimens met acceptance criteria, where the minimum shear strength has to be like 29 megapascal, and the laser surface texturing has resulted in more than this particular benchmark. In the second functionality is basically why not simply replace the powder coat with surface texturing. So in this use case, in this particular use case, we also investigated this. So for example, the powder coat has a roughness of about 76 microns, and different roughnesses like deterministic textures like channels and pillars are fabricated with similar roughness. And these particular textures were investigated for frictional properties between the foam block, which represents the bone, and also the laser textured titanium alloys. And both microchannel and micropillar textures, as shown in this table, have performed really well compared to the powder coat structures, which shows the biocompatibility of the laser surface textures. And finally, these demonstrators were prepared. For example, here the stem and cup are shown. These are the CAD drawings of the cup and stem. And finally, these are placed in the SYNTECS machine as shown here and started machining. And on the right side, we can see different roughnesses are achieved on the stem of the implant as shown in the right side of the figure. And the stitching mark shows differences between the smooth transition between different patches on the stem implant.